and he'll be talking about transport in dilute magnetic semiconductor heterostructures.
Stick. Hi. So I'd like to hopefully end well before time, because even I'm tired since the 9th of this month. We have been having relentless lectures and school talks. Okay, so I'm going to talk about transport in dilute magnetic semiconductor heterostructures. This we have been doing for about 2 years now. And my co-workers are Kusum Dochak, who is my student in TIFR. The samples have been grown by Boris Aronzon at Kurchatov, and the resistivity measurements also have been performed at Kurchatov. Then we have noise measurements, which are done at the high magnet lab in high magnetic field lab in Toulouse. And theory has been developed by Kusum, myself, and Clement Kugel. So we are very grateful for discussions with Meilikov, Kemet in Simon Fraser, Tibushev, Deepak Dhar, Dima Khmelnitsky, and T.V. Ramakrishnan. And some of the work I will present today has been reported in this paper, and we are funded by Department of Science and Technology and RFBR and Euromagnet. DAE, yeah, TIFR, yeah. 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 So here's the brief outline. I'll first give a very quick rush through ferromagnetism, discovery of ferromagnetism in bulk eminent doped semiconductors. And I must add that to this day there is a big dispute over what's the mechanism of ferromagnetism in these materials, especially in cases where they are less conducting. Then I briefly describe non-magnetic delta doped heterostructures, because ultimately our goal is to have delta doped Mn heterostructures, so magnetic heterostructures. So for that we have some discussion of non-magnetic cases first. And finally, I introduce DMS heterostructures, compare our devices to the existing ones, and I show how these are these have got very good mobility. They are quite two-dimensional, and they show strong signs of ferromagnetic correlations. And in particular, we are interested in the insulating samples, and it will become clear why that's the case, not just because it's easier for us to do calculations at this moment. In the insulating samples at low carrier density, we have phase separation, and we have a model of describing how these inhomogeneities come about as a competition of disorder and nonlinear screening. And finally, we model the ferromagnetic correlations into this thing decided by Coulomb largely, and discuss resistivity and noise in this context and compare them with experiment. Okay, so this is the first I know reporting discovery of ferromagnetism in Mn doped semiconductors. This is Mn in indium arsenide. And so here's one of the graphs from the paper. It shows the Hall constant as a function of temperature, and the Hall constant has been fit to such, could be my mobile. So Hall constant has been plotted as a function of temperature, and the fitting is to an empirical law of this kind. There's a constant part, and there's a part that is proportional to resistivity times the susceptibility. This is the anomalous Hall part, and the linear dependence on resistivity shows that some mechanism called skew symmetric scattering mechanism describes this quite well. Those are details we are not interested in, but the main thing is chi here, which can be extracted. And so if you extract your chi out of it, you can fit it very beautifully to a Curie-Weiss law with Curie temperature of 3.8 kelvins. And this is another set of plots from the same paper. It shows the remnant Hall effect. As you turn off the magnetic field, you still have some Hall constant left. That's coming from magnetization here. So this is the anomalous part then showing up, and the remnant part survives up till about 7 kelvins or 8 kelvins. And here is a direct measurement of magnetization, also showing a comparable sort of onset of. So this is also the remnant magnetization as a function of temperature, and shows a similar temperature scale for eminence. Well, this is chi, yeah, so in a way, yeah. This one, I think often the samples are very small, and that causes difficulties. So suppose you have a tiny sample in a ton of other stuff, then somehow they managed to do it. I don't know the details of this one, but it was probably not easy. But most commonly, this is how it is done in mesoscopic systems. You extract it out of transport. Because your sample is probably some microns across and it's buried in a huge bulk of other stuff, and whatever magnetization measurements you do will be more or less dominated by the rest, rather than what's happening in this tiny thing very deep down. So we want to discuss DMS in the context of heterostructures. Why? Because, well, first of all, it gives us these structures. Let me describe and then say why. So these structures are made of sandwiches, and in this case the sandwich is between gallium arsenide and aluminium gallium arsenide, and this is the interface between the two materials. Then considerable distance from this layer you have some donors, silicon for example, and if you make a schematic of how the potential looks as you go into the device in this direction. From the top, you have these conduction and valence bands of gallium arsenide, and this is for aluminium gallium arsenide, and here's the silicon donors. And so the donors lose electrons to this conduction band. It shows a dip here because you have to keep the chemical potential equal across the two materials, and whenever the bottom of the conduction band dips below the Fermi energy, you acquire electrons here, and that's the source of your two-dimensional electrons, because they are confined in this direction, but they can freely move in the direction perpendicular. And you can move the bottom of the conduction electron band through a gate potential applied here. So this gives us great control over the electron density. And if you are studying magnetic phenomena which you think are triggered by, mediated by electrons, then this is a nice way to control the electron density. And furthermore, this can easily be made into devices where you can control the spin polarization ultimately when you have magnetic doping here through gate voltages. So incidentally, these heterostructures were key to the discovery of the fractional quantum Hall effect, and the main reason why these devices are created and they are useful is the physical separation of the dopants and the transport layer means that scattering of carriers here is relatively low than bulk, and gives you very high mobilities. Okay, so DMS heterostructures are relatively new, and here's the first one. So here what these people have done is, so they have a gallium arsenide and a beryllium doped aluminium gallium arsenide here, and schematically the structure looks like this. The quantum well is formed on the side of manganese doping. The manganese is like 0.3 monolayers in density, and it's separated from the interface by some distance ds, and there are various values which the experimentalists have used in the fabrication. And so this kind of is a self-defeating heterostructure, because here the localization of the wave function, sort of the wave function overlaps quite strongly with the manganese dopants, and it will have very low mobilities. For example, these samples have a typical mobility of 2 centimeters square per volt seconds, as opposed to 10 to the power of 5 for the gallium arsenide devices I showed you. So it's that bad. Nevertheless, you do have a controllable kind of system where you can control control magnetism through gate voltages. But here the plot I have selected is how resistivity looks like as a function of distance of this interface from the manganese doping layer. And so when manganese doping layer is very close to the interface, then you have these pronounced anomalies in the resistivity. And when the manganese layer is very far off, you lose these features, indicating that these may have something to do with ferromagnetism induced by the manganese. Yeah, unfortunately it forms on this side, and it gives very low mobilities. Okay, so my collaborators have a way out. They have a different kind of heterostructure. The doping is again in gallium arsenide, but here we have an indium gallium arsenide quantum well, and this separation is comparable to the previous picture I showed by the other groups. And the good thing about it is that, I'll show you later, that the two-dimensional whole gas is formed on this side. It has much less overlap with the manganese delta layer. And here I have also got a carbon delta layer, which provides holes without providing any kind of magnetism. So this is kind of a control thing, or you can use this to give a different background hole density in your quantum well. Okay, so here's some of the devices generated by my collaborators, and so these are like delta dopings of manganese through a considerable range, so ranging from 1.2 monolayers to a third of a monolayer. And the mobility correspondingly varies quite a lot. It's low here because of heavy doping. The ionization of these results in more scattering centers, and therefore you have lower mobilities. But even with the lower mobilities, you can see that even at low temperatures, our mobilities, except for maybe this sample, which is 100 times more than the previous ones I described, but usually they are well more than 1,000 times. So these devices are much better. But now let's see if they are ferromagnetic also, because it's possible to get higher mobilities by just moving the manganese layer very far away, but that gets rid of ferromagnetism as well. Yeah. So what happens is, like, manganese can get ionized to a greater percentage than that, but a lot of the holes go towards other stuff like compensating the internal electric field, all sorts of things. So, but the manganese ionizations we estimated are still not very high, they are low, like few percent. So to show that these devices are indeed two-dimensional, so in one of them, for example, the sample 3, here's a measurement of the resistance as a function of magnetic field. It shows classic two-dimensional weak localization, which was first studied by Altshuler, Khmelnytsky, Larkin, and Lee in 1980. Incidentally, this is one story the Russians got, which the Gang of Four hadn't, and the negative magnetoresistance. Yeah. So, yeah, okay. Yeah. Yeah, so, okay, I stop defending them now. Yeah. You also see Shubnikov-Dehas oscillations as you increase the magnetic field, which is, but you don't see them if you put your magnetic field parallel to the device, which is also an evidence of two-dimensionality. So the negative magnetoresistance is consistent with 2D weak localization, and Shubnikov-Dehas also perpendicular the plane. And finally, quantum Hall effect is seen in all the samples, including the insulating ones. So these devices are indeed two-dimensional. Okay, now the resistance. So all of them except the purely carbon doped one, which is this one, shown here for control reasons, show anomalies or shoulders at some characteristic temperature, which is roughly like in the same ballpark range, not varying much. Even though the carrier densities have been varying, the doping density is varying. There is some change here systematically, but not that strongly. And so these we believe then are, or suspect at this point, that these are probably due to ferromagnetic correlations. Sample 1 and 4 also show hysteresis in magnetization at low temperatures. And now finally, anomalous Hall effect is observed in all the samples. I think the barrier is not that big in this case. So we estimated like what is the tail of the wave function from the quantum well reaching out to the manganese layer, and assuming certain thickness from the manganese layer, we found that the overlap is about 1%. So because the barrier is not that high there. In gallium arsenide devices, it's quite different. This would be a very big, relatively big separation.
So the quantum well acts like a probe.
The quantum well has most of the holes.
So it acts like a probe.
Yeah, it kind of, we believe it's sort of responding to the magnetization and its dynamics in the manganese layer.
And that's delta layer means one single layer.
Delta means one single layer. So this is the most clear-cut evidence for ferromagnetism. This is anomalous Hall effect. So this is the most heavily doped sample, and saturation of anomalous Hall effect as a function of magnetic field shows that this has gone ferromagnetic, and it's at a relatively high temperature of 45 kelvins that it, in fact, we don't have data on yet higher temperatures. Maybe it went ferromagnetic even higher, but see that these temperatures are way above the temperatures at which anomalies in the resistivity are seen, which are around 20-25 Kelvin. We are seeing anomalous Hall effect saturation at way high much higher temperatures, except in the most metallic sample, where the anomalous Hall effect is still trying to saturate at 32 Kelvins, and presumably hasn't gone ferromagnetic yet. Anomalous Hall effect measures magnetization. So the Hall constant is proportional to m, and it happens when you have both some kind of ferromagnetism and spin orbit scattering. So Luttinger and Karplus, so they have the first paper on this. Then there are other mechanisms also involving side jump and skew symmetric scattering, but that will take me very far from this, but I can sit down with you and discuss. Yeah. Okay, so that's evidence that onset of ferromagnetism is at a relatively higher temperature than what is indicated by the resistivity anomalies. So here is very simple-minded modeling now. We essentially follow Gergel and Souris and many other people after that, and just use that kind of phenomenology for such devices, and rough numbers we obtain from experiment, from people who grow the devices and from measurements, etc. So this is how it crudely looks. Here's the MN dopant layer. It's separated from this left side of the quantum well by a distance lambda, and you have a quantum well of thickness W. In our case, this is about 10 nanometers, and this is 3 nanometers. And on top of that, you have, because the Mn atoms are randomly ionized, they create a random potential in the quantum well. So every now and then you have the fluctuation potential dipping below the average quantum well potential. Of course, you have the other thing oppositely also. And so the total potential also you should have the RMS fluctuation added to it. So whenever you get these depths, that's where the holes tend to first accumulate when you start populating it. Okay, so schematically a wave function typically will look like this. It will have some overlap with the Mn atoms here. And okay. So the modeling is as follows. We kind of subtract off all backgrounds and absorb that in the average potential well, and then say that on top of that there are Gaussian fluctuations of the ionized manganese distribution, and we just assume this white noise distribution by Fiat. Maybe like better approximations are available, but this suffices for some simple-minded treatment for the understanding of charge inhomogeneities in the two-dimensional quantum well. So let's see what happens. So let me look at the potential fluctuation due to this kind of distribution in an area of radius r. Let's say the potential fluctuation has happened here, and directly below it I'm looking at the quantum well. And so this will have a charge density fluctuation of the order of doping density divided by, not doping density, but ionized Mn density divided by pi r squared, where r is the size of the patch I'm interested in. Now, in this area, if I have a certain population of holes that matches this RMS fluctuation, then such potential fluctuations will tend to get screened out. Okay, so and also all potential fluctuations on a length scale larger than this. So that's the idea, that if you put holes in the system, they screen out all short range kind of potentials, and this gives us some kind of a characteristic length for this non-linear screening. Okay, one can easily work out the fluctuation potential. This is the RMS value, and it depends on the device parameters and doping density, dielectric constant, etc., etc. And this is the characteristic screening length we have corresponding to a hole density P. Notice that if my density becomes larger, the screening length becomes smaller. This is okay. And then this lambda is the distance from the quantum well. And this Z actually is this distance, because the wave function doesn't exactly sit here. It's largely centered around some Z naught inside the quantum well. So we are looking at potential fluctuations at that scale. Okay, so then what people typically do here is, because the confinement is strongest in this direction, and you need to first have a wave function here localized, otherwise the quantum well will not get populated at all. So you actually need bound states in the transverse directions first. So you solve the Schrodinger equation, which includes the potential fluctuations, and you look for negative energy solutions for the Schrodinger equation, and that is the subband energy, and you need them negative. Okay. So once you have got those, we find that, okay, for the parameters available to us, 2 subbands are populated in some samples, and in one there is just 1 subband populated. One can actually follow a very clever set of arguments to estimate what's the size of these charge puddles without doing much numerics, in fact any numerics. So the rough idea, which goes to Gergel and Souris and later to Shklovsky and Efros, goes like this. Suppose I look at the potential fluctuations on a length scale RPN, which is the length scale of the puddle size, let's say. So it will have some fluctuation potential which has created a well. I start populating it with holes and fill it up to some maximum level, which I label by K max. I mean, this is very simple-minded, some wave vector of transverse quantization. And I say, okay, the virial theorem allows me to form such a relationship between the two. And this is like estimating the energy from the bottom of the potential fluctuation. Now, when I have 2 subbands, I can actually say that the droplet charge is distributed over these 2, and the lower equation shows that the total charge in the droplet, which is the fluctuation charge at this length scale, is distributed over these 2 subbands. So charge in the 2 subbands, I just add them up together. And this one shows that the difference in K maxes, so this is the K max, and for the quantum well of subband 2, it is a much smaller K max than for subband 1. The difference is just E2 minus E1, the difference of binding energies at K equals to 0. Okay, so one can then go and estimate the puddle sizes, and one finds that the samples are actually relatively close to the percolation metal insulator transition. And so in fact, one of the samples is metallic, the rest are insulating but are very close to the metal insulator transition. We don't guarantee this because it's a very crude estimate, so some amount of, except for the most metallic and most insulating, we remain a bit ambivalent. Nevertheless, it's fairly close. Then following Mott and Davis and Boychakov, etc., in 2003, we obtain a very simple expression for resistivity. One can do other things also, not just this one. And we just do this for modeling. And this guy is basically the correlation between spin polarizations in different puddles. Note that these are not dictated by sort of dynamics in this layer. Basically, there is a big cloud of Mn hovering over, and in general, it will have magnetic correlations which are typically at low temperatures on a much longer length scale. Nevertheless, it will have fluctuations of magnetization, and therefore, puddles lying directly under corresponding manganese polarizations will show alignment like this because of wave function overlap. And so the resistivity then is sensitive to the angle between polarizations in the puddles. But this is not the mechanism of ferromagnetism. These are just responding to ferromagnetism in the manganese. Okay, so now let me go back to where I was motivating the purpose of such discussion, which is like ultimately we want to understand the mechanism of ferromagnetism in these devices. So one thing we managed to rule out quite early on is that ferromagnetism, whether it is motivated, whether it is mediated by quantum well holes. So you have a Mn layer here, and you have a quantum well here, and in general you can have RKKY interaction mediated through this quantum well holes between 2 Mn atoms. But this is not supported by experiment, and so we look for interactions within the Mn layer, which is then going to be a bit like bulk, which brings us to the question whether it is due to an RKKY interaction of the Mn atoms mediated by holes here, and this will be similar to proposal for bulk DMSs by Dietel, and it has been supported by a number of photoemission studies in bulk which show both localized spins and itinerant carriers, and finally at least one ab initio study I know of. Then more recently there has been a spate of works motivated by literature in manganites and double perovskites that suggests maybe you don't have an RKKY mechanism here. What you have is an impurity band of Mn holes that sits above, a bit above the top of the valence band, and you essentially have double exchange ferromagnetism. And this is supported by ab initio studies of Priya Mahadevan, who is probably in the crowd, and many others. And lately I found some experimental evidence supporting this as well. So finally there is yet another proposal which is essentially double exchange, but at very weak ionization of the Mn dopants. This is a Polaron picture of Das Sharma and Kaminsky. So the idea is that whenever you have holes at the polarized Mn atoms, they overlap with a lot of Mn atoms here, and because of double exchange they all get polarized in some way. Then you have another hole here which has maybe a weak overlap with this fellow or no overlap at all, say at high temperatures, and this may be polarized in some different direction. And when the temperature is low enough, these start overlapping, and at a certain temperature they percolate, and that's the onset of ferromagnetism on a long length scale. So this is the Polaron picture. Okay, so maybe you could tell me who then, because I just don't know. I'm relatively new to this, so as you. Okay. So the point is that resistivity anomaly can be explained with any of these mechanisms. It depends. So in the end, all these models can be mapped under certain circumstances to some Heisenberg model, and you forget about dynamics. It's just JSI.Sj kind of models, maybe with some anisotropy, and each of them will successfully explain this resistivity anomaly. So for example, you can choose to have a 2D Heisenberg ferromagnet which actually never orders until you go to absolute zero, and at low temperatures, below the Curie temperature, you have an exponentially increasing correlation length. And alternatively, because of the geometry, you can have a uniaxial 2D ferromagnet kind of thing. And this does go to some kind of Ising ferromagnetic state, but if the anisotropy is small, this transition temperature could be quite low, and so you could still have appreciable region where it's essentially 2D isotropic Heisenberg physics, but ultimately it can go ferromagnetic. So this is a fit to the isotropic Heisenberg model, and as you can see, the data kind of can be relatively well explained by fits of very crude, simple-minded modeling of this kind. We can extract transition temperatures, Curie temperatures, and generally we notice that the Curie temperatures tend to be higher than the point at which the resistivity anomaly appears. And the reason is not that hard to see. So the reason is that the resistivity shows the maximum change whenever the correlation length becomes long enough that it becomes comparable to the interdroplet distance. So it doesn't have to go to infinity. So whenever this magnetic correlation length in the Mn layer becomes comparable to the interdroplet distance, you have a much easier hopping of charges and much less scattering. After that, you can go on increasing your magnetic correlation length, but it has relatively less effect on the transport. So it is a so the anomaly of resistance doesn't tell you about Tc. It depends on Tc, but doesn't give you a measure of Tc. and it will in general in these 2D systems lie below the actual Curie temperature. This is different from 3D because in 3D the correlation length will diverge at the Curie temperature, and so you should have the resistivity anomaly pretty close and a bit above Tc. Okay, so notice that this mismatch between the position of the resistivity anomaly and the Curie temperature had also been anticipated in the anomalous Hall measurements which I showed you earlier, which means the thing goes substantially ferromagnetic, relatively high temperatures. The anomalies don't capture it right then, for the reasons described. Now let me show you some of the data on noise. This is sample 4, which is quite close to a metal insulator transition, and to us it looks like more on the insulating side. If you might remember, the resistivity curve was all along insulating for this one, although at a smaller value and a smaller rate of increase than the insulating sample 1. And here this is a plot of the power spectral density times frequency. So it's kind of F times SF. SF is the resistivity noise, and it shows a highly non-monotonous behavior. And at low frequencies, this function goes roughly linearly in F at low temperatures, and at high temperatures, it kind of looks like F to the power of minus 0.5. Okay, so the characteristic temperature is around 13 hertz, and it's not a 1 over F dependence. And our first suspicion is, shall we try a random telegraph? Okay, that will go linearly with F at low frequencies. At high frequencies, it should have gone like 1 over F, but we don't have that here. And Griffiths, on the other hand, because of the stretched exponential relaxation, should actually go like F to the power of minus 0.5 at high frequencies, but then Griffiths is not really relevant for high frequencies, right? So, okay, here's the temperature dependence. This is much more noisy, and we really are not very successful, as you will see, with modeling these, but roughly they show the same characteristic features as the resistivity. The good thing about noise is that whenever resistivity has changed just by 50%, the noise manages to change by 2 orders of magnitude. Okay, so what causes this noise? We have analyzed 2 possible sources. One is the fluctuation of charge in these puddles itself, and the other one is fluctuations of orientations of magnetization. The fluctuation of charge has been studied in other contexts, like in manganites, where you also can have charge inhomogeneities, and the resistivity noise can be worked out. It gives you a kind of telegraph noise with a characteristic scale determined by activation energies, the ordering, as well as attempt frequency of getting out of the puddles, localization length, all sorts of things. Notice that this scattering rate is not really the function we used for resistivity. In fact, there was a sign difference here. Nevertheless, it depends on the same kind of quantities. But unfortunately, we find that this doesn't explain the data, meaning we cannot find any reasonable values of ECJ to account for the data. We can take unphysical values and sometimes manage to fit. So we started looking for resistivity noise due to ferromagnetic fluctuations. I don't have time to show how we obtained an expression relating magnetization fluctuations to resistivity noise, but it's fairly simple, and it depends on the autocorrelation function of the magnetization, which of course by the fluctuation dissipation theorem is related to the imaginary part of the response function, which is the dynamical susceptibility. Okay, so now this this dynamical susceptibility is quite sensitive to the mechanism of ferromagnetism. Without this dynamical part, you can get an effective Heisenberg model description for just about any of those scenarios. But this part actually cares about how the ferromagnetism came about. Had it been double exchange, it would show a completely different gamma of q omega than the RKKY model. So, well, I'll be showing you two different classes. One is where there is no conserved order parameter, such as the Ising or anisotropic Heisenberg model. And then there's another one where the order parameter is conserved, such as a uniaxial ferromagnet or an isotropic Heisenberg ferromagnet. These classes are sort of the same as those discussed in this monumental review by Hohenberg and Halprin. And in case of model A, the damping of the dynamical spin susceptibility is kind of independent of q and omega at small q and omega. And for conserved spin dynamics, it goes like the square of the wave vector. Okay, so first I try to fit the frequency data. So in case of model A, I will get a telegraph noise. In case of model B, I'll get something different. But with this range available here, where so much of data is being attempted to be shown, I can fit it with both. So it does make me very happy. So both model A and model B seem to be doing fine here. But things get better if I go to low frequencies or long times. So I can take the Fourier transform of the data and look at the long time behavior. And in this case, I've just shown the matching with model B dynamics. This is a fit to 1 over t plus some small logarithmic term which comes from 1 over f background. But it's very well described by model B dynamics over a wide range of wide range of noise. And likewise, we have tried to fit it with Griffiths and random telegraph. They give much poorer fits. Double exchange also I tried. It does not fit. Okay, so as I warned you, the temperature dependence, we do a much poorer job, not just because of wide scatter in the data, but for reasons I don't understand. We get the rough behavior like this, and the parameters we extract out of it are of the order of the resistivity extracted values. But nevertheless, this is one area where I have not been that happy. Okay, now in all this, I have completely ignored what is evidently there all the time, which is strong disorder in the manganese layers. Nevertheless, how did I manage to get such a fine fit to the model B dynamics of a uniform Heisenberg ferromagnet? Which one? Okay, so it's insulating here. Okay, but here, even if it's insulating, Dietel, etc., have been arguing for some time that if the localization length is long enough to encompass a large number of Mn atoms, then the RKKY arguments still go forth, and so one need not look into double exchange even there. Okay, but I'm not even like sure of what's going on there. I'm just trying to just fit the expectations of different dynamical susceptibility models. Yeah.
Point is, these models A, B, and C, don't they care about whether you do or do not have low-lying particle or excitation that which a magnet indicate?
So in case of double exchange, that is definitely due to the splitting, the decay is very suppressed, and likewise for the Heisenberg, for the RKKY case, those are available. So indeed for the RKKY case, the decay rate is much higher, and somehow it fits the RKKY much better than double exchange. The double exchange gamma is a much higher power law of Q in 2D. In fact, it's Q to the power of 6. And that will give me a noise that goes like 1 over t to the power of minus 0.4, which is way off the mark. Like it doesn't agree with the data.
So if the particle would indicate the magna, what classification will it belong to? I think that is
Yeah. So here it seems to agree with conserved spin dynamics. And if you ask me like why microscopically, I haven't yet sorted that out. It's just like very much of a phenomenological fit. But you saw that even the model A, although more inferior, wasn't that terribly bad. But only when I looked at the long time behavior or the very low frequency behavior, I realized that the model B fit is actually much better. Okay? And double exchange also doesn't fit. Okay, so argument for disorder is that, okay, disorder degrades spin stiffness and the Curie temperature, but provided that the disorder is not extreme, which I'll just qualify later, the form of the susceptibility and dynamics can remain unchanged until you are above this so-called classical percolation threshold. Now what I mean by this is, you start taking manganese atoms out randomly in the Heisenberg model, and you ask in the two-dimensional story, under what circumstances I can no longer describe the correlation function as an exponential behavior with some modified TC, and I have to completely look at a disordered story or a completely different universality class. So this this confidence stems from much older works by Brooks, Harris, and Kirkpatrick in 1977. This is diluted site Heisenberg model. Weinrib and Halperin on Heisenberg's model with correlated patches of TC, so spatially varying TC. And in the context of 2D Heisenberg model by Aronowitz and Lubensky. And more recently, Das Sharma and Pryor have done numerical simulations, and they found that yes, there is degradation of TC and Curie temperature, but you still basically have Brooks-Harris going through fine. And I'm thankful to TVR for bringing to my attention many of these works which were done when he was young. Yeah, when I was just about born, yeah. Yeah. So here's the summary of my talk. So I showed how at low carrier density you can have competition of disorder and nonlinear screening, which can cause formation of charge puddles in the quantum well. And I showed you how the resistance anomaly can arise when the magnetic correlation length becomes comparable with a relevant length scale, and it's not related necessarily, it's not equal to the 2D transition temperature, Curie temperature. Okay? So, and in fact in 2D we never have a phase transition, yet we see an anomaly. So in 2D, okay, this I showed, and then the resistance is non-1 over F over a large window of frequencies, and very phenomenologically it's in reasonable agreement with conserved or diffusive spin dynamics of a Heisenberg ferromagnet. And unlike resistivity, I showed you how noise is sensitive to magnetization dynamics and can probe into the mechanism of ferromagnetism. Thank you.
Since we had quite a few questions during the talk, maybe a couple of quick questions. Yeah. Vikram, this noise, if you just quickly go back to the slide where it showed temperature dependence, that there was a peak in temperature dependence. No,
Yeah.
no, noise, not this one, the one which you showed earlier. And no, even earlier. Right, little more. Yeah. Oh, this is a frequency at different temperatures, right? So you actually said that peak in noise. You discarded the trapping, detrapping, or sort of generation recombination noise.
Exactly, because okay, for two reasons. First, I was trying to use the same order of magnitude of parameters as explained as the resistivity data was completely explained with, yeah. And in fact, I could only obtain a fit with a negative value of charging energy. That made no physical sense to me at all. And the other thing was, later on I discovered that the data is not exactly looking like random telegraph. So it's looking more like 1 over T. It's looking like a power law. And there is a 1 over F background also, but it's much smaller. It's presumably coming from all sorts of other sources, including some remote centers which have trapped and untrapped charges, all sorts of things contributing the 1 over F.
Okay, at the end my question really was that the fact that you see a peak in frequency dependence means that there is some characteristic time scale. I do not know where is it coming from, but there is some characteristic time scale. So my question is that where is the time scale coming from?
Yeah, so okay, so I haven't shown you the low and high frequency behavior for the model B dynamics, but like I could after the talk show you how you get non-monotonous behavior, not only from model A, which is straightforward, it's telegraph noise, sizing like, but also for model B. And so I can show you, but at the moment I don't have a slide showing the non-monotonous behavior.
Great. Last, really a comment rather than a question.
Yeah.
So if you actually want to establish that this is a magnetic origin, spin fluctuations, I think the best thing to do would be what Arup said in his last talk. It's essentially look at the correlation in noise. If you can, because it's all long-range correlation that gives to a non-Gaussian features. So that's really the best way to check it.
Fine. Yeah. Fine. Take it. Yeah.
Any other questions?
You know, in this kind of system, there should be that what you call RKKE is actually a fluctuation one, namely mesoscopic when you calculate not a pair but twice. Does it important here as well? Then this interaction is much more longer because it is carried by two diffusion correlators.
Presumably, because simple-minded RKKY actually gives very low transition temperature, very low Curie temperatures, and people have suggested mechanisms of the kind you mentioned, that you can have much longer range interactions if you consider pairs. Yeah, but I haven't tried any microscopic modeling as you see. It's just trying to understand in very phenomenological terms what does the noise dynamic seem to tell us about phenomenology.
And just my next door colleague Sinova and as well his co-authors Alan McDonald and so on, they also think that all that is due to the just indirect exchange, etc., but definitely not use any kind of sophisticated argument like that. So probably there should be something else which convince them that exchange is coming in this way, but not through this double.
Yeah, must be. In fact, somebody told me some time back that Alan MacDonald, etc., have concluded that it's RKKY. It's probably not reported in any publication, which it is. Okay, so maybe I can get that from you. So I'd just love to know how.
One last question.
I have a short question.
Yeah.
See, in your setup, charges are depleted from the manganese layer. As you say, that some of them get trapped, some of them are trapped to the conducting layer. So then the nature of magnetism will be different from bulk gallium arsenide with magnesium doping.
Could be.
Because where the carriers are in the same region.
Could be, yeah. Absolutely. But here, the suspicion is that these holes are not playing much of a role. As you saw, many devices with different values of this carrier density, they showed no real difference in characteristic temperature where you saw the resistivity anomaly. That's a big turn-off for people who are looking at mechanisms of ferromagnetism mediated by holes here. In particular, if you have a strongly insulating state in the hole, the RKK interaction should have got exponentially smaller. So then the idea is that it's like bulk story, but in yeah.
Okay, so let's thank Vikram again. And